Hello, so just a heads up to anyone with photosensitive epilepsy, there are some strobing elements throughout this presentation. This is at 2 hertz or less. Um, so if that is something that might trigger your photosensitive epilepsy, you might want to sit this out or minimize the window for the next 10 minutes or so. With that said, this next slide and the following slides will have some strobing elements. So let us begin. So hello everybody, my name is Lynn, and as the title of the talk implies, I'm here to show you this little side project of mine that I've worked on for a while that lets you build a digital logic circuit in a bitmap image. The inputs and outputs of this language are bitmap images, and what you're looking at right now is actually a simple circuit inside of this language. So before I can show you much more about this language, I want to do a quick little refresher on digital logic circuits. So digital logic circuits, or boolean operators as you might know them, are kind of the basic building blocks of circuits that we have. These 4 operators, AND, XOR, OR, and NOT, are kind of a basic mathematical toolbox that you can use when operating with bits or booleans in programming, or with wires when making actual, little logic circuits. With this as our kind of toolbox, we can put these together and create memory cells. We can store data, do Boolean functions, and it's enough to make what we call Turing complete. This is really rad because you can build it up to create calculators, computers, any cool thing you might imagine. Now, when I was taking a digital logics course, I was also playing a lot of Minecraft. Minecraft has this feature called Redstone that also lets you make circuits, and it's also Turing complete. Kind of the intended purpose of Redstone in Minecraft is to create, automated farms or automated doorways, and you can also create computers and calculators in it because, again, it's Turing complete. And people have done that. I highly recommend maybe you search it up on YouTube or something when you have free time because it's really cool what some people can do in it. But I was playing Minecraft, building my farm, and I thought to myself, hey, I have this little diagram that I'm working with as I debug my farm, but it'd be really useful if I could just execute, run them. And I kept that idea in my head. I eventually finished that course, stopped playing Minecraft, and started getting really into, other programming languages. And I thought, hey, it'd be really cool if I could, continue with that idea. I want to be able to execute this bitmap image. And so I created what I call Riso. So what you're looking at here is actually the diagram actually the logo of Riso, and it's also a circuit inside the Riso language. You're looking at a circuit that's being executed, or an animation of a circuit that was executed. I'm not going to explain what every part of this is, and especially because during the stream, you probably can't see every element individually. We zoom in, there's some elements here that are, very small to the eye. But there's an explanation of what's going on in the logo in the Git repository. But I want to show you now how to actually build circuits inside of this language. Re-implement those 4 gates that we saw. So I'm going to shrink the logo and go over the basic elements of this. So first, we want to be able to store and transmit logical values, ons or offs. And so there are wires. There's 3 colors of the wires: lime, sapphire, and orange, so that you can make a kind of colorful, pretty circuits, and also so that you can cross them diagonally. Because see, if a blue wire and an orange wire touch one another, if a blue wire and a blue wire touch one another, then that'll just be one wire, and you can't have that. They're not insulated, but they are insulated from one another when they cross diagonally. We also need logic. So we have dark and light teal for logical AND and logical XOR, and this is enough for us. And I have a fan going. Let me turn that off. Logical AND and logical XOR. But while this circuit diagram will have logic flowing from left to right, we still need a way in general to define directionality, inputs and outputs. So we add two more colors to our palette, dark and light purple for input and output. So we have these two gates here, and we're finally able to actually put things into our logic gates, which is really great. And you'll see the inputs and outputs. For example, the AND gate, if you look, you'll notice that when all the three inputs are on, bright, the AND output is on one time step later. That means timing is really difficult and you have to work with it, which we'll see later on. You can also use these to implement the other two logic gates that we want, not and or. For not, you just put an input and an output next to one another. And for or, you put an input and output next to one another. For not, you put a 1, an on input, straight into the input to an XOR. And then you can use the XOR as a not gate by just adding one more input to that. So there's one big problem here that I haven't been able to solve yet, is that Riso is not super accessible. If you're colorblind or you have any vision problems, this might be really difficult. And even if you aren't colorblind, a problem I had was that the logical ands and the line wires are too similar in terms of color to one another on some monitors. So that's something I'm still trying to fix. Earlier versions of this had a textual representation of the circuit that would make it, easier to use in, whatever text editor you use. I haven't re-implemented that yet. But some of the original goals with Riso have still kind of followed through. I kind of wanted to be like Python in that it's kind of simple enough. It's kind of like an executed pseudocode, or in this case, diagram or sketch. And I also wanted to be like C in that the syntax of the language is kind of small enough to fit in one's head. If you've worked with C for maybe a year, you might remember almost every nook and cranny of the language, short of actually being able to write machine code, and even then. Because all the other digital logic tools I worked with, while way more useful and much faster than this, were kind of a pain to use. Now, this is also a pain, but I have an excuse that I'm not selling this for profit. Now, I want to, now that we have these 4 gates, we have our toolbox, and I want to show you a game of life circuit that I tried to make. Now, if you haven't seen Game of Life before, Conway's Game of Life, I should say, it looks kind of like this. You have all these cells that you can set up, and it's kind of this cellular automata that's meant to simulate what maybe a petri dish might look like. There's this one thing that's kind of iconic in Conway's Game of Life, a digital glider, or just a glider, that does this kind of thing. It repeats in a pattern of sliding downwards and to the right. Now, this here is not my project. This is copy.sh/life's implementation of Conway's Game of Life. Definitely go check out Game of Life if you've not seen it before. But back to this. I learned when making this Game of Life circuit that, again, didn't work. That timing is really important and it's really hard to do. To repeat, the goal was to create this kind of glider that went down the screen. That was my, what I really wanted to see, and I couldn't get done in time for Bang Bang Con because it was really hard, but I think the end result was really pretty. What you're looking at here is a 16:9 grid of Game of Life cells. If we zoom in, we can see some of the detail in the circuits. Here I have adders around the periphery of each cell that bundle together to the more complicated Game of Life logic. Now, there's some problems here that I haven't been able to bang out. This is the kind of the later iterations aren't shown here, so you might actually spot some problems, say in the SR latch. If you've seen these before, you know that both of these lines aren't supposed to be on at once. But if I show you the execution, and this is the part that has strobing at the full screen at 1 Hertz. If we show the execution, you'll see immediately things that aren't supposed to happen in Conway's Game of Life. We're not supposed to have everything disappear, then come back, and then flash like this. But this was really satisfying for me to see the values push forward through each gate, or each wire, just seeing them passed along. Now, thankfully, unlike my digital logic course, I will not be getting a grade from Bing Bing Con for the quality of my circuits. And when everything flashes on and off like it's not supposed to do, I don't have to feel too much anxiety about failing a class. At any rate, that's all I have for you here today. If you want to see the source code, I have a link to the GitLab and Emir on GitHub. If you have any questions or anything you want to ask me, feel free to contact me on Discord. I have the Discord here, but I haven't looked too closely at it for questions. So if you ask me, actually, I don't think I have time to answer questions during the presentation, so I'll be in the Discord. I'm also, you can contact me on Twitter as well. And also, if you make anything in this, I would really, really love to see that. I think that would be awesome. And that is all I have for you today. Thank you so much for watching, and I hope you have a great rest of your Bing Bing Con 2021. Bye-bye.